Alright, we're going to go ahead and get started with our next lecture video on electronegativity. Let's first start out with defining what electronegativity is. Essentially, you can think of electronegativity as the ability of an atom to attract shared electrons to itself. Or you can kind of look at it this way. In many cases, two atoms that are going to form a chemical bond between themselves, they're going to do so by sharing their valence electrons. And so you can think of electronegativity as the ability or the desire of an atom to attract those bonding electrons to itself. Let me diagram this to make it a little bit clearer for you. Let's say that we have an atom over here. Oops, I don't want to highlight. Say we have an atom, and it has a proton in its nucleus, and it's going to bond to another atom, and it does so by overlapping the electron shells, and it has also a nucleus. The electrons that are going to be shared between these two atoms are going to represent by these circles or dots here, and these are therefore the shared electrons. So the nucleuses of these two atoms are essentially sharing both of these electrons that are depicted here. Now, the electronegativity value is going to help us determine which one of these two atoms has a stronger attraction for these two bonding electrons. And what we find is the higher the electronegative value, the stronger or the greater the desire for that atom to attract the bonding electrons or hold on to those shared electrons with a greater strength. All right. One way that this works is by the number of protons. Let's say that the nucleus is the same distance between those shared electrons. But this nucleus over here has an additional proton. Well, if it has more protons in the nucleus, but the distance isn't changing, then which atom is going to have a greater attraction for those shared electrons? Well, obviously the one that has the most protons. The more protons a nucleus has, the stronger the attraction for those bonding electrons that will take place, as long as the distance between both nucleuses are the same to those bonding electrons. All right? So hopefully that illustration will help out a little bit here. All right, now let's take and look at specifically the periodic trend that occurs with electronegativity. In your notes, I have placed a periodic table that gives the values or the electronegativity values in each one of those boxes along with their symbol. If you look closely at this table, you will notice that there are no noble gases listed, and that is because the noble gases do not have electronegativity values, which means that simply that the noble gases do not form chemical bonds. They have no desire for attracting electrons, or simply no attraction of bonding electrons whatsoever. So they don't have a value here. All right? Now, take a close look. What is the trend do you see as you move across a period? If you look closely, you should see that the electronegativity value is going to increase as we move across. It should get bigger. Why is this the case? Why is this occurring? Well, simply the electronegative value increases as the atomic number increases in a given period, and this is a result of the greater effective nuclear charge. Remember that as we're moving across the periodic table in a period left to right, that the number of protons increases, and as the number of protons increase, so does the effective nuclear charge. And so this is going to impact the electronegativity values, or there will be an increase in attraction force of the nucleus which therefore strengthens the attraction of the valence or the shared electrons. Okay? Kind of look at this in terms of oxygen and carbon. Carbon's electronegative value is 2.5. It's smaller than oxygen's 3.5 electronegative value. So why does oxygen have a higher electronegative value? Well, it's simply because oxygen has a greater effective nuclear charge. It has more protons in the nucleus. So oxygen is going to attract bonding electrons with a greater strength than carbon will. All right? So now let's look at the trend as we go down the periodic table within a group. What happens? What do you notice? Well, you should notice that the electronegativity value is going to get smaller as we move down the periodic table. If you look at group 1, for instance, you will notice that lithium has a higher electronegative value than francium and all the others. So we can say essentially electronegativity increases as we go up the table. Now, why does this occur? Well, it goes back to the fact that electron shells are being added as we're moving down the periodic table. And as we're adding electron shells, this is going to change the attraction for those bonding electrons. The electronegativity increases as the atomic number. Oh, we need to change that. That's not correct. There's a typo here. Crossed increase out. And we need to change that to decrease. All right? Now we'll make it correct for us. So, essentially, the electronegativity decreases as the atomic number increases down a group. This is a result of an increased number of energy shells or levels, which increases the distance over which the nucleus must pull on the shared electrons, reducing the attraction. All right, so let's take a look at sodium versus rubidium. Now, sodium has a larger electronegativity value, meaning it has a greater attraction for bonding electrons. Why? Well, because sodium has only 3 energy shells, whereas rubidium has 5 energy shells. And so the bonding electrons in rubidium would be much further away than they are for sodium. And so sodium has a greater attraction for those bonding electrons if they occur. You can see the same thing for oxygen and for sulfur. Oxygen has a higher electronegative value because it basically has only 2 shells, where sulfur has 3 shells. And so the protons in the nucleus for oxygen is going to have a stronger attraction for bonding electrons than sulfur will because of the 3 shells that sulfur has. Simply the 3 shells, the bonding electrons are going to be further away from the nucleus of sulfur and can attract them as strongly as oxygen will. All right? So these electronegativity trends on the periodic table are very important for you to know. So make sure you come to class with that knowledge. Okay, we're going to look at one more thing, and that is there are ways in which we can use electronegativity values to simply help us to determine what type of bond is going to be formed. All right? If electronegativity values are essentially the same, in other words, there's going to be no difference in electronegativity value, negativity. Okay, I'm running out of room. Essentially get the idea. Then it will be considered a nonpolar covalent bond. That that will be formed. Okay. Now, if the electronegativity difference, so the difference is up to 1.8, then we would call this a polar covalent bond. So if you take the difference between the two atoms that are forming a bond, and the difference in electronegativity values is greater than 0 but up to 1.8, then we consider it a polar covalent bond. All right? Makes sense? Okay. Now for ionic bonding, if the electronegativity difference here is greater than 1.8, then the bond is considered ionic. All right. Now we're going to look at this electronegativity in greater detail when it comes to bonding types later on in our lecture videos. But for now, this kind of gives you an idea that we can use electronegativity in some degree to determine the type of bond that's going to be made between two different atoms. All right, so we're well over time, so we're going to end our lecture video here. And so remember to study hard, and if you need to relook at this video again, then please do so.